When the AC grid goes down, the equipment designed to protect and restore it requires power to operate. That power comes from the substation's DC battery system. It's the absolute last line of defense, standing between a temporary fault and a catastrophic blackout. Bringing one of these systems online necessitates a multi-phase validation of both chemical energy storage and active power electronics. The procedures are governed by a massive, overlapping framework of international standards, pulling testing requirements from the IEC, IEEE, and NEMA. When a project specification, the manufacturer's specific instructions, and these international standards conflict, technicians must apply the most stringent rule. Whatever protocol demands the highest standard of safety or performance is the one that gets executed. Rigorous, documented adherence to this hierarchy establishes a verifiable baseline of reliability before the system is ever called upon in an emergency. To execute these physical tests, we rely on a specific set of primary diagnostic tools: a hydrometer to measure fluid density, a calibrated digital voltmeter, an internal resistance tester, and a DC load bank to simulate electrical demand. This commissioning document dictates the strict 5-point physical safety protocol that must be enacted before a technician even approaches the live battery rack. First, technicians implement lockout-tagout, or LOTO, protocols on the main circuit breakers to completely isolate the system from the rest of the substation. Next, they establish hard, safe distance boundaries using physical barricades and warning tape. Third, the environment requires highly specialized personal protective equipment. This includes Class 0 arc flash gloves, protective eyewear, and high-visibility clothing. The final physical prerequisite is the implementation of proper temporary equipment grounding to safely redirect any stray fault currents. These absolute safety prerequisites establish the controlled environment necessary to conduct empirical testing on hazardous chemical systems. Once safe access is established, the validation begins with a mechanical inspection of the battery rack. Every cell's polarity, the physical integrity of its connecting links, and the torque marks on the bolts must be explicitly confirmed. This schematic highlights the next step: measuring the initial open circuit voltage of every single cell using a digital multimeter. This establishes our baseline and must be done before any charging occurs. We then move to chemical diagnostics, using the hydrometer to read the specific gravity of the electrolyte inside each individual cell. Because electrolyte density fluctuates with heat, specific gravity is strictly dependent on ambient temperature. Technicians must log the room temperature to accurately interpret these chemical readings. After applying an initial charge to the bank, both the open circuit voltage and specific gravity measurements are repeated. Comparing these two datasets isolates any weak or abnormal cells. Testing the internal resistance of the cells requires an essential mechanical step first. The individual cell links must be physically disconnected. Measuring internal resistance across a fully connected bank yields dangerously invalid data, as the parallel electrical pathways mask the true resistance of the individual unit. This granular cell-by-cell mapping establishes the static, chemical, and electrical baseline. Only when this baseline is verified can we safely authorize dynamic load testing. To prove the chemical bank can sustain prolonged grid-down conditions, we run a 10-hour capacity test. But first, the operational log must confirm the battery bank has not been discharged within the previous 7 days. As shown in this discharge test diagram, absolute isolation is required. After measuring the initial float voltage, the charger must be physically disconnected from the battery bank by opening the circuit breaker.
The DC load bank is connected, and its discharge rate is programmed. These parameters are strictly derived from the manufacturer's ampere-hour capacity rating, scaled for a 10-hour duration. During execution, the load bank pulls a constant current draw. Over the next 10 hours, technicians periodically log both the total bank voltage and the individual cell voltages as they steadily degrade. At the end of the test period, these final unit voltages are cross-referenced against the manufacturer's accepted end voltage charts. Surviving this sustained stress test provides the empirical proof that the chemical storage can independently hold the substation online during a catastrophic blackout. With the chemical storage verified, the focus shifts to the active power electronics, the AC to DC battery charger. The charger is set to float mode, and the DC load bank is connected to its output to simulate variable grid loads. The unit is then stressed based on the simulated load through 5 stages: 0%, 25, 50, 75, and finally 100% of its rated capacity. At every single one of those load steps, technicians measure the 3-phase AC input voltages and currents. The manual details calculating total AC input power from 3-phase measurements. Comparing DC output against AC input derives overall efficiency. It also highlights measuring DC output ripple voltage, requiring a multimeter on DC terminals set to read AC. Crucially, the battery itself must remain mechanically disconnected during this step. A connected battery acts as a massive capacitor, which would smooth out the ripple and skew the true output results of the charger. The 50 and 100% load steps are then repeated, but this time with the charger forced into boost or equalize mode. Verifying this efficiency and strictly limiting any alternating current ripple on the DC line is vital to protect the substation's delicate, microprocessor-based protection relays from long-term degradation. Beyond power conversion, we have to verify the charger's logic controls. This means checking the human-machine interface to ensure its protective alarms trigger correctly. As shown on this panel schematic, the first step is executing a simple lamp test to confirm all visual LED indicators are physically operational. From there, technicians use specialized high-impedance simulation links to safely induce positive and negative ground faults. There is a strict operational warning here. You must never create a dead permanent ground fault on a live DC system during simulation. It creates an immediate arc hazard and can severely damage the relays. As these faults are safely simulated, a correlation check is performed. The values displayed on the charger's internal screen are cross-referenced against independent readings from calibrated multimeters to ensure the onboard computer is reporting accurate data. The remaining functional logic checks simulate high and low DC voltages, AC input failures, current limit triggers, and the system's soft start behavior. These logic tests confirm that the charger's internal systems will accurately report and react to any real-world electrical anomaly. If any discrepancies appear on the interface, or if chemical anomalies were found before the discharge test, they must be recorded in the exception register and physically resolved before the system can be signed off. Once everything passes, restoration begins. The mandatory first step is the physical removal of all temporary simulation links, ground faults, and external load banks. The main battery bank is then mechanically reconnected to the charger, and all tripped test alarms are manually reset.
Finally, the entire DC system is returned to its approved normal float operating mode. Reaching this zero-alarm, fully restored state marks the end of the validation process, leaving the substation with a verified and operational power source.